Hello, everyone. Good morning, good afternoon, as the case may be, depending on where you are. And welcome to this Ophir Photonics webinar. My name is Mark Slutsky, Product Manager for Power and Energy Measurement Solutions here at Ophir Photonics. And thank you for joining us today. As you probably know, we host webinars pretty regularly and we put up videos and things like that. This webinar will be different in that, in fact, I would even say usually by part of my introduction to most of our webinars is where I explain how I'm trying to keep the information as generic as possible so that it'll be as helpful as possible to, as wide an audience as possible. But when it comes to using actual examples of real life solutions, I'll be referring to Ophir products because those are the ones I'm able to talk about. Today's webinar is a little bit different. We're actually focusing on one very specific product. And the reason for that, to be perfectly honest, is just that it's unique. It's very interesting. It presents a very, I would say, elegant solution to not only, well, to my pleasant surprise, not only to the very specific problems that we had in mind when we developed it, but it turns out that it solves a whole bunch of additional problems as well. And so we wanted to just share it with whoever is interested in how something like this might be able to help. So with all that in mind, let's begin. The product we're talking about is something called the Ariel. Just before we begin, on a more logistical note, the total time of our conversation today should be relatively short, probably like 30, maybe 40 minutes, something like that. Questions and comments are welcome. If you have any questions or comments, please use the text chat box on the right side of your screen, and I'll respond either in real time or at a suitable point in the flow of the information. And if I'm already saying that, I'll just add that you can, of course, contact us offline as well. I'll be leaving my contact information up on the final slide for a minute or two after we conclude in case you want to get in touch with me offline. I assume you have some degree of contact with Ophir, or you wouldn't be here today. You can contact us through our website, through our either Ophir office or our partner in your, depending on what country you're in. On every page of our website at the bottom, there's a contact us form. I forget what we call it, request support, request a solution, ask an expert. I don't remember what we call it, but we do try to make it as easy as possible for you to get in contact with us if there's any way at all in which we can help you. So with that, let's press forward. I assume you're somewhat familiar with Ophir. As you probably know, whether you're already a customer of Ophir or are evaluating or are just interested in the subject matter, Ophir, some years back, we were acquired by Newport, and some years after that, Newport, along with Ophir, became part of MKS Instruments. I think the best way I can summarize all of the text on that slide a moment ago is that we like to do the hard things that you would prefer to get off your head so that you can focus on your work where you bring your added value and not have to lose any sleep over the tools that you're going to need to use to help you get your work done. I would say that's a fair summary of what it said there. So the instrument that we're talking about is called the Ariel. If you're familiar with Ophir from the past, you may know that our products, at least our major products, tend to have names that are somehow related to astronomy. We have the Nova and the Vega and the Pulsar and Quasar and all sorts of and Helios and things like that. So this product is called Ariel. I like to joke, half joke, that when we announced it, it was really named after my then newborn grandson, whose name is Ariel. But no, it turns out that Ariel is also an astronomical object. It's one of the moons of the planet, I believe, Neptune, if I'm not mistaken. So here's what we're going to talk about. We're going to look at what problems it's here to help you solve, why we developed the Ariel, a high altitude, as I like to say, overview of what it is, basic review of how it works. Not going into any great engineering depth, interesting as it is, but just the principle behind it, and you'll appreciate why I'm emphasizing that when we get to there. How you use it, not in the sense of a detailed, instruction manual. It's not a complicated instrument to use, but there's way more specific functions and features than we would want to cover in the course of this sort of a discussion. But in principle, how we use it, because there are a few main ways that it can be used. Again, you'll appreciate why I'm emphasizing all this when we get to it. And a quick look at the main highlights of the data sheet of the specifications, and just a few main bullets of what interesting things this solution brings you that might be of particular interest. Okay, that's what we're going to be covering. So let's begin with why this thing exists. What problems is it here to help you solve? So the basic typical usage scenario of the Ariel would be some sort of an industrial high power beam measurement in a situation where the space is limited. It's either inaccessible or accessible with difficulty, tight space, no option for water cooling or fan cooling. So the thing has to be able to work in a tight space, measuring a high power beam, but without needing water or even fan cooling. And you may wonder, well, then how would you do that? Haha, okay, we will see. A very good example would be inside an additive manufacturing chamber. It's not accessible during the measurement itself. Most likely the chamber door is going to be closed when the measurement actually takes place. Pretty clear that there's no water cooling infrastructure. You can't really use fan cooling because then you'd be blowing all the powder, all the process material all over the place. And because it's inside a chamber with the door closed, you can look through the window of the chamber door to see the measurement result, maybe, but you can't reach in there to press buttons. It's not like the more typical handheld laser power meter where you've got a meter, an instrument in your hand, a sensor on the optical bench, and you press the buttons. It's not quite like that. So this is pretty much the typical standard model usage scenario that was in front of our eyes when we developed the Ariel. As I sort of hinted by way of introduction, it turns out that there's many other scenarios where the Ariel also is of great interest, even though it wasn't what we had, they weren't what we had in mind. We'll touch on those briefly when we do that review of the notable benefits. But the classic usage scenario is probably best illustrated by an additive manufacturing chamber. Okay, let's have a quick general overview of the Ariel. This is what it looks like. You can't quite get an appreciation for the size just by looking at the image, but it fits in the palm of your hand. It's about the size of a tennis ball. If you look at any of the short videos that we have on the Ariel webpage on our website, you'll see it being held in a child's hand, and you'll get a better idea of just how compact it is. So it's an industrial laser power meter that measures high power beams. It's self-contained, meaning as opposed to that typical, laboratory type instrument that I just described a moment ago, handheld or desktop meter, and the sensor mounted on a standard optical bench with the mounting base and the mounting rod. This is not like that. It's self-contained. As you can see, it has a readout display on the front panel of the instrument, but it can also be used wirelessly using a built-in Bluetooth interface. That would probably be the most typical way of using this. You may notice that there are buttons here on the front panel. Those are not the typical way of using it, but they are an option. So it's self-contained. It's meant to be used when you can't reach the panel, but it can also be used when you can, yes, reach the panel. There's also a USB-C connector. It's on the other side of the device in this photograph, so you can't see it. Usually that would be used more for initial setup and configuration. It certainly could be used connected by USB to a laptop, no question. The standard PC software that we have as our workhorse software application for all our regular instruments certainly is compatible with this. As I said, it's probably not the typical way of using the Ariel. It's one way of using the Ariel. 7 by 7 by 8 centimeters, no water cooling. It's dust proof, it's splash proof. It would have to be if it's going to sit inside an additive manufacturing process chamber and survive the experience. And it has a very fast response. You get the readout 3 seconds after the laser exposure. And the laser exposure itself can be very short, as short as 50 milliseconds and up to a couple of seconds, I believe 3, if I remember correctly, which already gives you an idea of how it's possible to measure high powers without needing cooling. You can already figure that the exposure to that high power is for a very short time. Excuse me. So the total amount of energy absorbed, and therefore the total amount of heat that's being generated, is actually not all that much. And the way this is typically used, before a process begins, you take a measurement of the laser power. If everything is okay, then you set up the workpiece. I mean, not the workpiece. You set up the work in the chamber, and you begin the process. And some time goes by before you're gonna need to repeat that. So the overall average power is going to be very low. The exposure to high power is for a very short time, and then there's plenty of time for the instrument to dissipate the heat by the time there'll be any reason to repeat the next, to get to the next measurement, so that the instrument doesn't actually heat up. Okay, how does this work? Again, briefly, we're not going into great engineering depth, but enough to appreciate the concept. Thermopile sensors are typically used to measure average power of a laser beam, and they're specified with a maximum rated power according to how well their body structure can continuously dissipate the heat that's being generated as the beam comes in. So for example, a sensor that's rated for up to 250 watts is able to dissipate heat at a rate of 250 watts. Now note that word continuously. If the exposure to high power is not continuous, if the sensor is only briefly exposed to the high power, as we said a moment ago, it can then take its time cooling off before another exposure. Treating this short exposure as if it were a single pulse and measuring the energy of that pulse gives us a way of using low or moderate power sensors to measure much higher powers by measuring the energy of the pulse and dividing by the known pulse width or exposure time. Power, remember, is energy divided by time. A joule per second is a watt. But we can make it easier than that by having the meter do the math for you. This can be particularly useful for measuring high power laser beams using a short exposure with a lower power sensor, or a sensor that's not equipped with water or fan cooling, which is what I'm going to refer to as a lower power sensor. So we actually have at Ophir a number of standard thermal sensors that were specifically given high energy scales for just this purpose. Here you see an example of one of them. it's able to dissipate, this particular sensor can dissipate power at a rate of, I believe, 35 watts, but it can handle 10 kilowatts, 10 kilojoules of energy in one pulse, as long as you then give it time to get rid of that heat. Now, dividing the energy by the time, of course, can be done. You take out your, well, nobody has calculators anymore. You take out your cell phone and open up the calculator app and divide by the known exposure time. This can be done semi-automatically, and by semi-automatically, I mean the way many of our meters at Ophir work, where in that particular mode, we call it pulsed power mode, the meter prompts you, the user, to enter the known exposure time, and then it divides the measured energy by the exposure time, and then it just does the math for you. Not, you know, a terribly big deal, but it's convenient. I'm just going to maybe share my screen for a moment to just show you what that looks like. Share content, screen, share. Here we are. Just this is one of our meters connected to a regular thermal sensor. And you'll notice it prompts you. You set it up the way you would set up a thermal sensor for regular single shot energy measurement. Okay, here I'm using a very low power sensor because that's what I was able to put on my desk to film this. It prompts the user to enter the pulse width, and then you fire the pulse and it says ready. Okay, and there you are. It gives you the readout in units of power. It's a very straightforward. Stop sharing. I'm back with you. So that's what I sort of refer to here as semi-automatically. Or automatically, by equipping the instrument with a built-in fast photodiode that measures the pulse width, the exposure time, automatically for more industrial applications. And that's what the Ariel does. It measures high power using a short exposure. It has a built-in fast photo detector to measure how short that short exposure is. And then it does the math for you. So here you see a readout in units of power, even though physically it measured the pulse energy. Okay, I mentioned that there's a few ways of using it. So first of all, very simple controls. Those are those three buttons that I measured, on, off, and also the main menu. The middle button toggles you through the menu items, and this is select. So you toggle through the menu until you get to the item that you want to select. You press that and select. No big deal. Display screen. So here you see the measurement results. This is a readout in kilowatts. By the way, it also displays the actual physically measured energy. You can actually do the math yourself. 895 joules divided by 133.3 milliseconds. That's the displayed exposure time, pulse width. It really is indeed 6.712 kilowatts. So this is actually a real result. So it displays the power readout. It displays the actual energy and exposure time measurements that were used to get to this power readout. And a whole bunch of status indicators, the current temperature of the sensor, Bluetooth status, what wavelength setting, which includes diffuser in, diffuser out. We're going to see that in a moment. And so on, battery indicator. And the settings. What energy range you're on, what mode you're in. We're going to come to the mode in a second also. It has a detachable anti-reflective coated window, protective window that helps keep it dust-proof and splash-proof. It also has a detachable diffuser, which lets you work with smaller beams that have a higher power density, higher energy density, so you can work in those kind of applications as well. So it's actually multiple instruments in one. You don't need two different devices. You just attach to the diffuser and it can withstand higher power densities, typical of high power, small diameter beams. There's a protective cover with a sort of a target on it so that it can help you more easily align the device inside, let's say, the process chamber. Here's that well, I hope you can see that. Here's that USB connector and an attached rubber plug to close the connector. We don't want process debris getting in there and clogging up the connector. From inside the connector, by the way, there's no opening into the rest of the interior of the device, so that the device itself is in any case safe, but we don't want to ruin the connector. And on the underside, there's a positioning hole and 4 mounting threaded mounting holes for a heat sink. We're going to come back to that heat sink in a moment. Oops, wrong button. Here we are. It can be used standalone, using the soft keys, the menu, the setting, everything using these 3 buttons. That works fine. And then you'll see the menu on the screen. You scroll through the menu using the toggle button, select, and so on. That's one way to use it, easy enough. You can use it wirelessly using the built-in Bluetooth interface, and it works with your Android device. We have an Android app that you can download from our website or from the Google Play Store. It's called Star Viewer. Here's just a few screenshots. You can control, fully run the measurement through your Android device. This is, I think, the most typical usage scenario for the Ariel. Or you can use it with the USB interface connected to a laptop or a PC, on which you would be running our standard Ophir PC software application, which we call StarLab. Both Star Viewer, the Android app, and the StarLab PC software application can be downloaded from a whole bunch of different places on our website. The one that's the most relevant now is at the bottom or near the bottom of the Ariel web page on our website. Under the in the middle of the page is a bunch of tabs: specifications, catalogs and manuals, software. So under the software tab, that's pretty intuitive. You can get to StarLab, and you can get to the Star Viewer Android app as well. As I said, you can also download Star Viewer from the Google Play Store. Quick look at some of the main specifications. Okay, I had mentioned that we're going to come back to that mode thing, so I just want to explain what that is, because this is actually quite interesting. There's a CW mode and a short pulse mode. Everything we described until now, short exposure to a high power beam, all that is the short pulse mode. By the way, I'm going to start with the second bullet first. In the short pulse mode, you can measure up to 8 kilowatts. But there's also a CW mode, which uses the more standard power measurement. And there you can measure from 200 milliwatts up to 30 watts continuously. In other words, the body design of the Ariel is able to dissipate heat just through conduction to the air at a rate of up to 30 watts. Above 30 watts and all the way up to 500 watts, you can still measure in this mode, but it needs to be intermittent, meaning for a minute at a time, 2 minutes at a time, half a minute at a time, depending. The idea is that you want the overall average power to not go above 30 watts, because otherwise you're putting in heat faster than the heat can go out. The device could heat up and then fail. At the maximum power in this CW mode, 500 watts, it needs to be quite intermittent, not more than 20 seconds at a time, and then you got to wait 2-3 minutes. I mean, you can do the math of how to arrive at that long overall average of 30 watts. But at 500 watts, it's 20 seconds and then a couple of minutes, probably a minute, 2, 3 to cool down. So those are the 2 modes. That icon over here, one of the settings that I pointed out, here you can see a pulse icon. So intuitively, that means that here it's in short pulse mode. It has a number of spectral ranges. With the anti-reflective coated protective window in place, You have two spectral regions. There's 440 to 550 nanometers and near IR 900 to 1100 nanometers. With the diffuser in, you have the same two spectral regions, except that the near IR is just a little bit narrower. Instead of starting at 900, with the diffuser in place, it starts only from 940. It can also operate with neither the diffuser or the protective window in place. And that gives you mid and far IR capabilities as well, which are blocked by the window and the diffuser. So you have, in addition to those, you also have 2.94 micrometers and 10.6 micrometers. The only thing is, when there's neither a protective window nor a diffuser, it means it's open, which means it's not dust-proof or splash-proof anymore. Something just one needs to keep in mind. And the fast photodiode that measures automatically the pulse width, the exposure time, is a silicon-based photodetector, and silicon does not see mid IR or far IR. So if you're going to work without the window because you need to work at an application in the mid IR or the far IR, you'll need to take out that cell phone calculator app and do the calculation manually. Okay, so again, this really is multiple instruments in one. I pointed out that one of the status indicators is the temperature. When do you need to pause for cooling? So what it says in the specifications is that you reach the maximum operating temperature, which, by the way, is 60 degrees Celsius. You reach that when you have a total cumulative exposure to 14 kilojoules. After a total of 14 kilojoules, the instrument, the Ariel, will have heated up to 60 degrees, and then it'll flash a warning. I don't have a picture of it. I don't remember what the warning says. I'm too hot. I need some time to cool down now. So for example, let's say you're measuring a 2 kilowatt beam, and let's say you're using a 0.7 second exposure. So 2 kilowatts times 0.7 seconds is 1.4 kilojoules per shot. 10 such shots is 14 kilojoules. Now, obviously, those 10 shots take half a day. You're not going to heat up to 60 degrees. Here I'm talking about where you do one after another, which is probably more typical. So then you're going to reach 60 degrees. The Ariel will tell you, wait, I'm too hot. Let me cool down. And then the cooling down time is approximately 10 minutes, but that 10 minutes can be reduced if we attach a heatsink to those 4 threaded heatsink mounting holes that we saw on the bottom of the Ariel. So I said we would come back to that. We did. So just a quick review of the benefits that the Ariel offers you. It's compact, it's dust resistant, splash resistant, it's rugged, it's designed for industrial use. Wireless, no cable. It can be put in for example, a process chamber and the door closed, and you can operate it from your Android device, or you can look through the window after having pressed the buttons on the front panel. All of those options are open. No water cooling, no fan cooling. The thing is small, fits in your hand. Very fast time to reading, 3 seconds after the exposure ends. And it has quite an impressive heat capacity so that it can take many measurements before finally, eventually reaching its maximal operating temperature and asking you to, whoa, let me cool down, please, for a couple minutes before you use me again. It's got that removable diffuser, the removable protective window, so it can operate with high power density small beams or regular beams or mid IR and far IR. So it really is multiple instruments in one, and even more instruments in one. It's got that continuous mode for lower powers. From 250 milliwatts up to 500 watts in that continuous mode. So it's yet another instrument all packed into one. Okay, so in summary, I said about 30 to 40 minutes. We're now at 30 minutes. I surprise myself sometimes. So we're talking about a small industrial high power measurement device designed particularly for tighter, inaccessible spaces, such as additive manufacturing chambers, or any situation where the idea of a small device with no cable and no water or fan cooling that can be operated wirelessly is of interest to you. We had a quick discussion, high altitude, of how it works, not the design of the electronics, but the idea of the high power, short exposure, what that concept is. We looked at the main specification highlights up to 8 kilowatts in short exposure mode, from 250 milliwatts up to 500 watts in regular mode. USB, wireless, Bluetooth, or looking at the front panel, no water cooling, no fan cooling, rugged, all the various options with the protective anti-reflection coated window, the diffuser, neither, so that opens up those additional spectral regions and so on. Okay, that was the quick overview of this very interesting instrument. As I said, we don't usually have these webinars about a specific instrument, but this solution is interesting enough that we felt, and this was the feedback that we were getting, that it warrants an overview because it can solve problems beyond the additive manufacturing chamber scenario that we specifically had in mind. And so we were pleasantly surprised by the interest from a whole range of other applications, more traditional, welding and cutting and drilling and those kind of things that don't necessarily operate in tight, inaccessible spaces, but still very much enjoy the fact that it can be operated wirelessly, doesn't need a cable, doesn't need water or fan cooling. Operating on an intermittent basis is quite fine in very many applications and scenarios. Okay, I hope this was interesting. If you have any questions you want to ask online, you have a few more seconds in which to do that. My name again is Mark Slutsky. I'm the product manager for power and energy measurement solutions here at Ophir Photonics. This is my email address, mark.slutsky@mksinst, that's short for mksinstruments.com. I'm going to leave this up for another half a minute or minute or so. As I said, if you want to contact me offline, you're more than welcome to do so. Contact us through our offices in your various countries or our partners, distributors, depending on where you're located, or just through our website. Thank you very much for being with us. Have a really nice rest of the day.